All right, today we're going to start chapter 4. And in chapter 4, we're going to use those things we learned about probabilities and create what's known as discrete distributions. So we're going to deal with probability distributions and see how to use those in lots of circumstances. Now, basically, the reason we're doing this is because decisions are made all the time because of probabilities. And we're going to learn how to do these, how to use probabilities to make decisions in a formal setting. But if you think about what you do in your day-to-day life, you're always constantly making decisions um, based on probabilities. For instance, you probably go out to the grocery store and don't think twice about getting in a major car accident. And that ability to go out and feel safe is a decision based on a probability. It's highly unlikely that you go out to the grocery store and you get in a car accident every time you go out. Well, the same thing is done in uh, in actual calculations. So here's what we're going to do. In this course, we're going to look at decision making based in some actual calculations. We're going to answer some questions about how to do this in general, and then we're going to answer some questions about how this would apply to insurance situations, and we're going to ask about questions that would apply to like games of chance, things like the lottery or casino games. And so those are the types of things we're going to look at in this class. We'll look at real formally how to use probabilities in some general calculations, in some insurance, and in games of chance like casino games and lottery and things of that nature. So we start out with the idea of a random variable. So we saw variables back in chapter 1. That's some sort of a thing that can take on different values, some characteristic that can take on different values. And a random variable is a variable whose values are determined by chance. So for instance, how many heads you get when you flip a coin 3 times. That's a variable that is determined by chance. You could have 0, 1, 2, or 3 heads when you flip a coin 3 times. Or if I roll a die and I look at the number on that die, that is a random variable. Okay, it's determined by chance. Or even like how far a dart is from a bullseye, so a distance of whatever. That's a variable that's determined by chance. Now, in this chapter, we're going to look at discrete random variables. Basically, we're just going to focus this chapter on variables that are both random and discrete. So they have a finite or a countable number of outcomes, excuse me. So for instance, my examples from earlier about rolling a die and that die landing on some number, that would be discrete because the only outcomes that are possible when we roll a single die are 1, 2, 3, 4, 5, and 6. Similarly, when you flip a coin 3 times, how many heads could I possibly get? Well, it's either 0, 1, 2, or 3. Okay, so only whole numbers, only finite or countable numbers are are available. Now, discrete random variables would not apply to something like I pick somebody out of the population at random and I look at their height. Because height is not discrete. We saw that earlier. We can always go out more decimal places with height, so it is not discrete. So height would obviously not be discrete. Although we could make it random. We pick somebody out in general and find a random person. But the discrete aspect would not apply to heights. Would apply to number of heads on 3 flips of coins, number on the face side of a die when you rolled it. Now, here's what we do with a discrete random variable. We create probability distributions. And in a lot of this section, we're going to create a lot of probability distributions. And what that is that's just a table that consists of possible values of a random variable and the corresponding probabilities. So if you think about where we saw that distribution earlier, we saw frequency distribution way back in chapter 2. And a frequency distribution is this list which has tables, it's a table that has classes in one list and frequencies in the other. Well, in a similar fashion, a discrete probability distribution is going to list out all of our outcomes and then the probabilities of each outcome. So let's do a couple of examples here. So first off, let's say we roll a die. So we're going to roll a single die. And I've oriented this probability distribution horizontally. You could have also oriented the probability distribution vertically. I tend to orient these horizontally just because there's more outcomes and it tends to look a little bit nicer. And then there's also another trick when we calculate averages that this will kind of play nicely with. So here's what I'm going to look at. So the outcomes of the die are 1, 2, 3, 4, 5, 6. Notice that the variable x here corresponds to these 6 outcomes. So variable x can come up as 1, 2, 3, 4, 5, or 6 when we roll a die. Now what's the probability of each of those outcomes? P of x. Well, if it's a fair die, then each probability is 1 in 6. That's just the standard classical probability that we saw back in chapter 3. So the chance that you roll a 2 is 1 in 6, the chance that you roll a 3 is 1 in 6, and so on and so forth. This is the other one I was talking about. What happens if we flip 3 coins, or we flip the same coin 3 times? Either way is acceptable. We want to figure out how many heads we get. So we let x be the number of times I get heads when I flip 3 coins. So again, x is my variable. And if you flip a coin 3 times, it is possible that all 3 times it comes out as tails. So you could get 0 heads. It's also possible that if you flip a coin 3 times, you could get 2 tails and 1 head. Or you could get, over here, 2 heads and 1 tail. Or you could get all 3 being heads and 0 tails. Now it turns out the probability in that case is not all the same. It turns out there's actually more ways to get 1 head and 2 tails than there is to just get 3 tails. So the probability of getting 3 tails is 0.125. The probability of getting 1 head, and that would imply 2 tails, is 0.375. Same thing, same probability for getting 2 heads, and then 0.125 is the chance that we get 3 heads. So this table is the probability distribution. Now here's another probability distribution example that we didn't do a whole lot of, but it does come up in various cases. So this is an example of what would happen in a game like craps. If you have not been to the casino and you don't know what craps is, basically it's a game where you roll 2 dice, and then instead of looking at the numbers individually on the dice, what you do is you take the sum of the numbers that show on the 2 dice. And so we're going to let x be the sum of numbers when you roll 2 dice. Now it turns out since each die has 6 possibilities, there are 6 times 6 or 36 different combinations of what you can land on in the numbers. So how many of those add to the number 2? Well, there's only one out of the 36 combinations that add to the number 2, and that's if both of our die are ones. So if I roll, let's say, a green and a red die. If the green die lands on a 1 and the red die lands on a 1, then the sum is 2. So there's one possibility out of 36 that we land on a 2. In terms of landing on a 3, well, the green die could land on a 1 and the red die could land on a 2. Or the green die could land on a 2 and the red die could land on a 1. And so there are 2 possibilities of 2 combinations that would add up to 3. By the way, there's a really nice visualization that you can take advantage to see how this probability distribution comes into play. And what I've done is I've created it in Excel, but you can draw this pretty very easy. Like I said, think about rolling 2 dice, one of them being red. Now the red die is always going to come out 1, 2, 3, 4, 5, or 6. And like I said, the other one is green. That green die will come out 1, 2, 3, 4, 5, or 6. And so I can draw this 6 by 6 grid inside here that takes into account the sums of each of those. So 1 and 1 is 2, and then you can clearly see how we get that 3 can occur twice. The red can be number 2, the green can be the number 1, or the green can be the number 2, and the red can be the number 1. And if you look at this grid closely, you'll see that obviously the diagonals give us certain summations. So 4 occurs 3 times because it occurs on that diagonal. 5 occurs here. Again, I'm only counting the inside because the insides are the sums. The red and the green are not the actual summation, but actually the outcomes of the single die. So 6 happens 1, 2, 3, 4, 5. 7 is the most common occurrence, and there are 6 of those. And then it starts going back down. 8 happens 5 times. 9 happens 4 times. 10 happens 3 times. 11 happens twice, and 12 happens once. And you can see, obviously, because there are 36 total possibilities, you can see each of the probabilities coming into play. Okay, so whenever you're dealing with rolling 2 dice and looking at the sum of the numbers on the die, you can draw that grid and fill it in fairly easily. Now, let's look at a few facts of what has to happen on each probability distribution. Now, this is actually the probability distribution that we looked at earlier. It's where I flip a coin 3 times or flip 3 coins and see how many heads there are. It turns out if I would have made those into fractions, the fractions would have been 1/8, 3/8, 3/8, and 1/8. Notice something about listing out all of these possible probabilities. First one, obviously the probabilities individually have to all be between 0 and 1 because they have to be legitimate probabilities. So for instance, 1/8, 3/8, 3/8, and 1/8, every single one of those numbers has to be between 0 and 1. Now obviously the outcomes, the variables, we have a variable which is 3. Obviously the variable itself doesn't have to be between 0 and 1, but the probabilities do. So all the probabilities have to be between between 0 and 1, and we have that in this probability distribution. The other one is sort of a collective argument. So we have an individual argument where each probability has to be between 0 and 1, and then we also have a collective fact that because I've listed out all of the outcomes that are possible, when I add up the probabilities, they should add up to be equal to 1. And if you notice this probability 1/8, 3/8, 3/8, and 1/8, 1, 3, 3, and 1, they all add up to 8/8, and that is 1. So the probabilities in this case do add to 1. By the way, if you go back and check that out in the previous examples, let's take a back step here. When you roll 2 dice, if you add up all of those numbers, all of those probabilities, they do add to 1. They add to 36/36. Here, this is exactly the same probability distribution we dealt with, but it's in decimal form instead of fraction form. And the probabilities add up to 1. Each one individually is between 0 and 1, and then collectively they add up to 1. Here, 1/6 6 times, yeah, that adds up to 1, and then each one individually is between 0 and 1. So we can use these two facts to tell if something is a legitimate probability distribution. So we're going to ask on these two tables, could each of these individually be a probability distribution? I want you to push pause, think about this. In 5 seconds, we'll come back and answer it. All right, so let's take this first table here. Could this first table, that top one, be a probability distribution? Now, don't get thrown off by the variables. The outcomes of the variables, we don't care if one of them's negative or 0 or 1 or 5. Remember, the outcomes don't matter, just the probabilities. Both of our facts are about probabilities. So let's check the individual fact first. 1/7, 3/7, 1/7, 2/7. Each of those is between 0 and 1. So individually, they're okay. So now let's check collectively. 1/7 plus 3/7 plus 1/7 plus 2/7, 1, 3, 1, 2. Yeah, that adds up to 7/7, which is 1. So that first table could be a probability distribution. That could be a legitimate probability distribution. So we'd say yes. Yes, it could be a probability distribution. Now the second one, 6, 7, 8, 9, that's no big deal. 2/8, 2/8, 5/8, and -1/8. This -1/8 fails the individual test. So because that probability is less than 0, this second table cannot be a probability distribution. So no, this second table could not be. Now I do want to point out the fact that notice that if you add up -1/8, 5/8, 2/8, and 2/8, they do add to 1. But that's sort of irrelevant because if we fail one of the facts, then it can't be a probability distribution, no matter what the second fact does. Again, push pause and look and determine if these can be probability distributions. All right, take a look at this this top one. This top table, 12, 13, 14, and 15. Notice that the probabilities of 0.3, 0.21, 0.45, and 0.04, each of those individually is okay. So what I'm going to do is I'm going to take out my calculator and just add them all together. 0.3 plus 0.21 plus 0.45 plus 0.04. And when I do that, I get precisely 1. So that top table, yes, can be a probability distribution. Now let's take a look at the bottom table. 0.32, 0.46, 0.28, and 0.29. Each one of those individually is perfectly okay. However, when you add them up, you get to a number which is bigger than 1. In fact, you get to 1.35. So that bottom table could not be a probability distribution. So the answer to the bottom part is a no. No, this cannot be a probability distribution for the second table there. So the first one is a yes, second one is a no. And again, notice that in the previous slide, we dealt with fractions for probabilities. In this slide, we dealt with decimals. Either's fine, but they both have to satisfy those two facts. Okay, so now that we've determined probabilities, we're going to, or excuse me, determined whether something could be a probability distribution. We're going to look to see how we could find an average, how we can find a mean from a probability distribution. Now we're going to go back to flipping 3 coins again. So we're going to flip 3 coins and we're going to ask ourselves, well, if you flip 3 coins, what's the average number of heads you're going to get? So we see the probability distribution there. Now, the way we got this probability distribution was in the following sense. We listed out all of the different sequences of 3 flips of a coin. So pretend that I flipped a coin 3 times. It is possible to get heads, then heads, then heads again. It's also possible to get 2 heads and 1 tails. Now notice that the 2 heads and 1 tails, there's 3 different sequences that could land on. The tails could come at the very end, it could come in the middle, or it could come at the very beginning of my sequence. Similarly, we could get 1 head, and that 1 head could come at the tail end, as means the end of the sequence, in the middle, or at the front of the sequence. And then there's only one way to get 3 tails in a row. So how do we find the average? Well, here's what we do. We pretend that each of these possibilities happened once. So let's pretend you did the experiment and I did the experiment and 6 other people did the experiment. So a total of 8 experiments happened. And each of us got one of these unique answers, one of these unique sequences. Well, how would we calculate the average number of heads here? What I would do is I'd say, well, this one had 3 heads, this one had 2 heads, this one had 2 heads, this one had 2 heads. So it's like 3, 2, 2, 2. This one had 1, this one had 1, this one had 1, and this one had 0. So we'd add up all of those, 3, 2, 2, 2, 1, 1, 1, 0. And then because we have 8 different sequences, we divide by 8. So that's all we do. 3 plus 2 plus 2 plus 2 plus 1 plus 1 plus 1 plus 0, and divide the whole thing by 8. Now, we can do a little bit of mathematical manipulation, and we can rewrite that to make it look a little bit nicer. So we can take 3, we did that 1 time, 2 happened 3 times, 1 happened 3 times, and 0 happened 1 time. So we could observe that and utilize multiplication instead of doing repeated addition. So instead of doing 2 plus 2 plus 2, we can just say, well, 2 happened 3 times. So that's going to be a total of 2 times 3. And because we're dividing by 8, well, I can divide each of these individually. The 3 times 1, I can divide that by 8. If I rewrite that, that just looks like 3 times 1/8. And the 2 times 3, all divided by 8, looks like 2 times 3/8. And then 1 times 3/8, and then 0 times 1/8. And if you notice what's happening here is I'm rewriting finding the mean as simply just taking each of the values multiplied times the probability of getting that value. So 2 times the probability of getting a 2. 1 times the probability of getting a 1. 0 times the probability of getting a 0. And then adding all of those up. And so one way we can find the mean is by simply taking each value, multiplying it times its corresponding probability, and then adding up all of those sums. That's what that capital sigma means, if you recall from chapter 2. So what I would like you to do is to push pause on the video, take a moment, and find the average of the following probability distribution. Let me explain what that means. Find the average of this probability distribution, and then I will come back and explain what it is. All right, so hopefully you did that. Hopefully you found the average of this probability distribution. Now, this probability distribution, by the way, came out of an experiment where I pick 5 people and I see how many sleep on their side, meaning instead of sleeping on their back, sleep on their side. And it says that 60% of the total population are side sleepers. So we're going to choose 5 and see how many of them sleep on their side. So obviously, there is a situation which none can sleep on their side. There's a situation where 1 of the 5 can sleep on their side. There's a situation where 2 of 5 can sleep on the side, and so on and so forth. All right. So if I were to do this by hand, well, I would have taken the 0 and then multiplied it by 0.0102. And then I would have taken and added 1 times 0.0768. And then I would have added 2 times 0.2304. I would have taken 3 times 0.3456 plus 4 times 0.2592 plus 5 multiplied by 0.0778. And rounding to 2 decimal places, I got 3.00. Now let me just show you how I did that. I'll write that out. I know I spoke through that, but let me write that out. I wrote that out on my chapter 4 guided notes. So the mean I got by taking 0 times its probability plus 1 times its probability plus 2 times its probability plus 3 times its probability plus 4 times its probability plus 5 times its probability. So basically, this is the other advantage of laying out my probability distribution, my discrete probability distribution horizontally, is I can take the x value times the probability and then put it down there. The x value times the probability, put it down there. The x value times its probability, put it down there, and so on and so forth. And we get out a 3. So using the formula by taking just x times the corresponding probabilities, we get that the average is 3. Now, there is a way to find standard deviation using probability distributions and doing it by hand, but it's way longer than we need. So what I'm going to do is I'm going to show you how to find the mean and the standard deviation using the calculator. Now I want to go back to saying that we're dealing with a probability distribution. And when we dealt with earlier in class, when we dealt with our other type of distribution, that was a frequency distribution, we just used one variable statistics with list 1 as my class list and L2 as my frequencies. Well, we're going to do the exact same thing. We're going to go back to the exact same typing that we dealt with in chapter 2. So if you need a refresher, you can go back and reference that video. I'm just going to talk through it. We were going to find the mean using the calculator. So we're going to put all of the x's in list 1. Remember how to get there, stat, edit, should be able to clear out list 1 and put 0, 1, 2, 3, 4, 5 in L1. And in list 2, type in the corresponding probabilities. I'm doing that right now. It takes just a couple of seconds. There's 6 of them. Make sure again that if in list 1 you're putting the 3, that in list 2 the 3 is right next to the 0.3456, and so on and so forth. Okay. Now, just like when we dealt with a frequency distribution, once we have all of the data into list 1 and list 2, we're going to go to one variable stats, and then depending on your operating system, it's going to either be L1 comma L2 or list L1 frequency list L2. Since we've done that in previous chapters, I'm not going to do that right now. I'm not going to display that right now, but you can see it for yourself. Now, one thing you'll see when you find the mean using the calculator, the mean, again, rounded to 2 decimal places, still comes out exactly the same. All right, it's 3.00. However, one weird thing that happens with the standard deviation, you should notice that on your calculator, remember, standard deviation of a sample was denoted by S, and standard deviation for a population was denoted by lowercase sigma. Let me get a lowercase sigma symbol in here if I can find it. There it is. Okay. And if you look on your calculator, there's actually no display of a sample standard deviation. However, there is a display for your population standard deviation. It should say that the population standard deviation is about 1.09535. I'll round that to 2 decimal places. That rounds to 1.10. So the population standard deviation is 1.10. The sample standard deviation is gone. Now, there's a reason for that. All right. Let me give it to you in 2 ways. First is the mathematical way. All right. So for the mathematical way, I'm going to jump back to when we talked about standard deviation back in chapter 2. And I want you to notice something about the n in your calculator. You should have an n equal 1 displayed on your calculator. What that means, that n is just standing for the sum of the probabilities. So if you think about it, what we just said earlier is that all of the probabilities have to add to 1. Well, if we're assuming that n is the sum of the probabilities, that gives me a big problem when I'm dealing with sample standard deviation, because the sum of the probabilities have to add to 1, and the denominator for a sample standard deviation is n minus 1. So if I put a 1 in there, 1 minus 1 would be 0. Dividing by 0 is an undefined mathematical object. We don't have that problem with the population standard deviation. With the population standard deviation, we're dividing by capital N. So dividing by 1 there is not a problem. However, with the sample standard deviation, dividing by 1 is a problem. So that's the mathematical reason that sample standard deviation is not displayed, but population is. Now, the sort of more intuitive explanation is to go back and think about what these probabilities represented. Or maybe it's easier to see in this example. This probability of 1/8 when we flipped a coin 3 times, and this probability of 3/8, probability of 1/8, that actually did not come from an experiment. So it did not come from a sample. It came from classical probability. And because it came from classical probability, it had to assume that this was basically coming out of a population. In other words, when we did this experiment, we didn't actually flip a coin 3 times 50 million times to get these probabilities. They came from the classical probability instance. So the long story short is we don't know the size of our sample. There's no such thing as the size of our sample when we're dealing with probability distributions. Okay, I don't have that data. Same thing with this. If we know we're choosing 5 people, we're doing this sort of theoretically, and therefore we don't know how many samples of size 5 we would have chose to get these probabilities. So because we don't have a sample size, we don't have a sample standard deviation, okay? And that also means that when I'm displaying the mean, instead of using just the word mean, what I could have done each time is find the actual symbol for mean in Microsoft Word. There it is. And I could have used the symbol mu. All right, since I know this is a population mean, I could have said mu equals 3.0. So when we're dealing with probability distributions, we're always going to be dealing with a population, both as a population mean and a population standard deviation. So when we're asked to calculate that, that's what we're asked to calculate. Population average and population standard deviation. All right. So let's go back and talk about real quick some different terminology. I've been talking about, well, we're trying to find the average. We're trying to find the mean. And in my last example, that would have been the average number of people who sleep on their side in a sample of 5 people. And what we should think about that is if each of us who've ever listened to this video went out and sampled 5 people and asked them to sleep on their side, my 5, there might be 1 person. In your 5, there might be 3 people. In somebody else's 5, there might be all 5 people who sleep on their side. But if we averaged all those numbers, they'd average up to about 3. So we said the average number of people who sleep on their side is 3. What we're going to do is we're going to switch the notation from average to expected value. Now, this is like switching from just y equals notation to function notation in basic algebra. You question yourself, well, why would you ever do this? Well, you do this, you switch notation from average to expected value for some advantages of how we write things and sort of for speed of writing things down. Okay, so expected value is simply another term for average. So the nice thing about expected value, again, it's kind of like the switch from average, y equals notation to function notation. The notation of expected value is going to be e of x, whatever that variable x happens to be. And you might think, well, that's more letters than just mu, right? We just had mu as our average earlier. But a lot of times when we get into insurance details, when we get into games of chance, we're not going to be caring so much about what it lands on, the actual numbers that the game of chance lands on, but we'll be asking ourselves, well, what is the expected payout? Or what is the expected profit? So we can easily switch our letter here with inside of expected value so that x can mean a lot of different things. And if we had to continually use this mu notation, we'd have to continually explain it every time. So now we can just switch the letter from x to y, from y to z, from z to a, and it always means expected value of x, the average value of x, the theoretical average. So here's what I'd like you to do. I'd like you to pause the video and find the expected value and the standard deviation of this probability distribution using your calculator. Hopefully you did that. So again, let me explain what I'm doing. In my list 1, we have the total outcomes. Notice that the outcomes are 0, 5, 10, and 20. So we have 4 different outcomes in list 1. In list 2, we got 0.3720, we got 0.3244, we got 0.2115, and we got 0.0921. So when I do stats, calculate one variable stats, list 1, list 2, again, depending on which operating system you have, is either L1 comma L2 or list L1 frequency list L2. So when I did this, I got that the expected value of x came out to about 5.58 and the standard deviation came out to about 5.91. Now let's think about this real quick. Oops, something went wrong there. Okay, so let's take a look, oops, at this in light of what we did, of what we just said. Okay, so notationally, here's what we would do. We would say the expected value of x is equal to 5.58, and the standard deviation, let me go standard deviation symbol. I would have just written this down had I been writing it by hand in my notes, 5.91. Okay, so the expected value, 5.58, and standard deviation, 5.91. Again, I'm rounding those two things to 2 decimal places. Now, what I want to point out to you is this. Notice that the expected value is not a possible value, is not a possible outcome in my experiment, right? 5.58 is not a possible outcome. And that is perfectly fine because remember, we're not saying what do I expect as an individual. We're saying if we did this experiment over and over and over and over and over again, and then we averaged all the outcomes, what would that average come out to? Well, that average would come out to about 5.58. I want to emphasize that point using one of our previous examples. One of our previous examples was this coin flip. In fact, let me look at it through this. That coin flip, well, how would I have found the average? I would have taken each of the x's, multiplied those probabilities, and then added them all up. Now, I didn't mention this before, because I just mentioned how do we find the mean. But I want you to notice that the average here came out to 1.5. How do we interpret that 1.5? That doesn't mean an individual is going to land on 1.5. What that means is if you had 50 people and I gave each of them 3 coins to flip, and each of the 50 people came out, some people would have probably gotten 0 heads, some people would have gotten 1 head, some people gotten 2 heads, some people gotten 3. But it's fairly likely that the average of all of those 50 people would have came out to about 1.5. Okay? So that's why the expected value is called the theoretical average. All right? So that's what the expected value is, this theoretical average. And again, we can find that in one of 2 ways. I could have either found that using my calculator, list 1, list 2, or I could have calculated 0 times this number times this probability, 5 times its probability, 10 times its probability, and 20 times its probability. Now, here's the interesting thing. It turns out that even though an individual can't land on the expected value number, that expected value number is actually more interesting because it can't be landed on. All right? It actually tells me something about the group as a whole. And whenever we're dealing with probabilities, whether it's insurance, whether it's lottery stuff, we are always concerned about, well, what would happen if this experiment ran a lot of times, so a great number of times. And so because we're so interested in that, that's what's going to lead us talking about what happens with insurance and what happens with games of chance. So right now we're going to stop the first part of these notes, the first part of 4.1, and I'll start another video about the insurance and games of chance expected value calculations.